Hey guys. Hello everyone. Welcome to Rust. Thank you for coming, thank you for being here. I hope you're all as excited as I am to learn some Rust. So yeah, this is kind of an overview of everything we have planned. Everything that we've prepared is at that link in the top right. That links to an MD book, which is like a kind of website. It's just a bunch of markdown files compiled and then put on the internet. Open it up, play around with it. Most of the code snippets in there can be run and edited, and I'd encourage you to do so. And the sources for that markdown are all on GitHub. The link to the GitHub is in the top right of the markdown book. So if you spot any errors, corrections, feel free to PR them in. So we've got 3 mini talks, which is 3 of these, where I'm just going to go through the content of what we've written. There's 3 sets of notes on there, which correspond to those 3 talks. And I'll just go through those, talk you through it. We've also got three little projects. We'll be doing tic-tac-toe later, which I know is really boring, but we thought, well, why do something really complicated and then just confuse you? We'll start simple and then build up from there. They'll be spread out over 4 workshop sessions. The last 2 will both be Ray Tracer, because that's quite a big project. Everything that I've written and I'm going to talk about is adapted from the book. And by the book, I mean the book is called The Rust Programming Language, so everyone just refers to it as the book. That is the ground source of truth. Go and check that out. It's absolutely fantastic. So that's some of the projects. So tic-tac-toe, we've got Chip 8. Next week, Chip 8 is kind of like an emulator for an old platform for building retro video games. It's quite a common first emulator project, and it's very cool. It's very cool. We've also written a little library to help out with that, so you just focus on the emulator and we'll handle the sound, all the windowing, all that. The Ray Tracer is a rewrite of ray tracing in one weekend, for anyone who's heard of that. So we're building our own graphics rendering engine and using a lot of neat little vector maths to put together something that can render that final image. So I should probably start out by at least motivating this whole thing to you. Why Rust? Why you should care about Rust even a little bit? Well, Rust is fast. It's in the same performance class as C, C++ for most use cases. It's got the same compilation model. It's compiled straight to binary with no runtime, just like they do. But usually that kind of performance comes with the trade-off of having to manage memory manually. You still have to manage memory manually in Rust, but it's a lot easier due to ownership rules enforced by the compiler, known as the borrow checker. It's entirely safe. Who's written a bit of C, C++ before? Who's ever had its segfault on them? Yeah, none of that, no more of that. In safe Rust, entire classes of memory and thread safety bugs just don't exist. There is unsafe Rust where you can segfault it, but we're not going to get into that. The type system of Rust, which is inspired by Haskell and ML type languages, is very functional, and it helps to make code safe too by enforcing that you get more things right at compile time in the type system. Who's familiar with Haskell, done a bit of Haskell? You'll probably find a lot of similar concepts going on here then, so hopefully that'll be helpful. It's also a joy to work with. People like Rust, so much so that it's Stack Overflow's most loved language for 8 years in a row now. The documentation is very thorough and consistent, and the language server makes writing code really easy. And error messages from the compiler are very friendly, very helpful. For those of you who've ever seen an error message from a C++ compiler, the Rust error messages are like a nice warm hug in comparison. It's like, oh, no, you got it wrong. It's okay. This is where you fix it. It's very, very helpful. Cargo, the package manager, is integrated into the language. And makes working with libraries really, really easy. There's lots of libraries on crates.io to do pretty much anything. Rust is also starting to be picked up by industry. Google are starting to use Rust for more and more. The entire Android Bluetooth stack is written in Rust, I believe. And at Meta, Facebook, Rust is a first-class language. They're starting to use it for command line stuff, I believe, and it's second only to Python and C++, and they're starting to replace a lot of their C++ code base with Rust. Meta actually rewrote their entire source control backend in Rust recently as well, and that was like a massive success. Also, recently support for writing Linux kernel modules in Rust has been merged in, and that will be released in the next kernel version 6.1. I don't know when that is. Soon? Soon. In the next few weeks, hopefully. And there's also some really cool work going on to write the GPU drivers for Apple Silicon in Rust for Linux. So for the rest of today, I'm basically going to deliver the equivalent of the first 6 weeks of CS118 in half an hour. I'm going to assume familiarity with basic programming constructs. So if you are a total newcomer to programming, you might struggle to keep up. But if you do want a more thorough rundown of any of the basics, please come talk to me. Is anyone not familiar with like most of those? Because that's what we're going to go through, and I'm going to just be like, okay, this is an if statement, let's move on. So if that's going to be too fast, then come and talk to me. I can point you at some more resources to help. If there's any other questions, please do stop me. I'm happy to take questions, go back and forth. I also have a habit of talking too quickly, so if I am talking too quickly, stop me and tell me to slow down. Feel free to follow along with the notes as well on the website. That's rs118.uwcs.co.uk, because all the code samples I'm going to show are the exact same as the notes, and you can follow along, edit them, play with them as I'm talking. So this is what hello world looks like. We use the fn keyword for a function declaration. Every Rust program will have a main because that's your entry point, same as C. And print line is how we put stuff in the console. Variables are declared or bound, as we say in Rust, using the let keyword. So let x equals 6, x now equals 6. Here with print line, we're using the format string feature to print the variable, so the curly brackets get replaced with the x. It's very similar to Python format strings, for those of you who know how those work. So in Rust, everything is immutable by default, including variables. So previously, we couldn't rebind x to anything else. X would always be 6. Everything's constant. If you want things to not be constant, we use the mut keyword, which is usually used to mark mutability. So anywhere a value can be mutated, it will be marked in the source code. So here you can see we're changing the value of x from 5 to 6, and we can do that because we bound it as mut. Try changing, if you've got the code open, remove the mut and see what error the compiler gives you. So these are your numeric types, defined by their bit width and signedness. So we've got, instead of just having char, short, int, long, and they are implementation defined and could be whatever size the compiler implementer may dream up. In Rust, these are fixed. Types are 8, 16, 32, 64, or 128 bits wide, and either signed or unsigned. Those bottom two are pointer sized. They're the size of a memory address on your system. They'll usually be 64 bits unless you're working with 32-bit systems for whatever reason. They're also used when you're talking about how big like a data structure is. So the size of an array is a U size. So like I said, chars are not, we have chars as well, they're not 8 bits wide. Chars are 4 bytes wide and represent a single Unicode value. So we can have like normal letters, and we can also have emoji or any other Unicode grapheme. So you can annotate let bindings with a type like so. That's usually not necessary because Rust's type inference is very good. So the only place you absolutely need type declarations is on functions. For variables, you generally don't. And if you do need one, the compiler will tell you, look, I don't know what type this is, please tell me. So there's top 3, it's fairly simple. Unsigned 16-bit int, signed 32-bit int, followed by char. 4th one down there is a string literal. We'll get to that later. 5th one down is a tuple. 6th one is an array. So tuples. Who's not familiar with tuples? That makes my life easy. Great. For those of you who might not know, they are like arrays, but the 2 types don't have to match. Or you can have 3 types, 4 types, and you declare each type explicitly. They're useful when you want to put 2, 3, 4, however many values, where you can only have 1. So for example, if you want to return a few values from a function, put them in a tuple. They're accessed using dot syntax, as shown on line 3 there. So you've got .0, .1, and you'll get the first and second values out of that tuple. They're 0 indexed, of course. You can also destructure them, as shown on line 4 there, and line 5. So that's kind of interesting because you can say let x, y equals tup, and then x will equal 1 and y will equal 2. Same below, c will equal a, I will equal minus 2. The underscore in the destructuring pattern, which is kind of what that syntax is called, means that the value will be discarded. So the 100.01 there, that will be discarded, it won't be bound to anything. That last line shows you like that, that 1 won't be bound, that line does absolutely nothing. Arrays are homogeneous, have a fixed length, and live on the stack. They're indexed using brackets, like most other languages, and the type signature is shown on the B binding there. So the type signature is the type of the array, semicolon, and then the number of elements in the array. The number of elements in an array is part of the type in Rust, which is really, really useful, so you can't really get out of bounds. Indexing can be enforced at compile time. But you can index out of bounds if you like using brackets. And if you do that, you will get a panic. Panics are Rust's way of throwing unrecoverable errors at runtime. And we'll kind of learn more about them as we go. So for example, that would just segfault in C. But in Rust, it'll go, actually, no, you've done something wrong. I'm going to stop and tell you. And the code will blow up, but at least you won't have caused a bug or an exploit. So we also have structs. Structures are basically the same as in C, C++. They're declared as shown, and they're made up of several name fields of different types. So that struct is a type representing a student, and the student has a name, an ID, a year, and if they're currently active or not as a Boolean. We can see an example of using that struct here. We declare a new one by initializing each field. We can't leave any of the fields uninitialized or blank. And we can also change the fields. We can access them, modify them, whatever. Because we've bound that struct as mutable, so either let mut u, that lets you mutate it. If we had bound it as immutable without the mut keyword, then we wouldn't be able to mutate any of the fields. The string bindings there, we're using string from to create a new string. Don't worry too much about string syntax now, I'll get to that later. Enums are our other composite data type. Enums restrict variables to a predefined finite set of named discrete values. It's short for enumeration because it enumerates all of the allowed options. So we have color, which is our type, and the 3 values of color are red, green, and blue. We can use the double colon syntax there to access the values of that enum. So color, colon, colon, red means we have a red color. We'll come across that double colon syntax a lot. It's used for namespacing enums and also getting into modules and stuff and crates. Lots of languages have support for enums like C and Java, but those are quite rudimentary enums. Rust enums are most similar to some types in functional languages such as Haskell and F#. So for those of you who are familiar with Haskell's data types, Rust enums are basically the same thing. So this is an example of showing what makes Rust enums so powerful and more similar to Haskell, is that the variants of the enum can contain values. This should look familiar to people who are familiar with Haskell. So this enum has 4 variants. The first variant is empty. It's just what we call a unit variant. That second variant contains a U32. The third variant contains a U32 and an I64, and that fourth one contains a string. So here's another example of an enum with some values representing some shapes. So we have a circle variant there that contains the radius of the circle in that U64 field. The rectangle variant there contains the length and width of the rectangle, and the triangle one contains the length of the 3 sides. You can see an example of how we declare, how we create a value of those different types there. It's like, we just put in the brackets. So this is a very special enum, one of my favorite enums. I have a favorite enum, wow. This is the option enum. It's basically a box, and that box can either be empty, none, or have something in it. It's generic over any type T, but we'll get to generics later, and most of you will be familiar with them anyway. Just think of the T as any type for now, anything that might be in that box. This enum is used an awful lot because Rust doesn't have a concept of null. There are no nulls in Rust. So no more null pointer exceptions, which is nice. But the trade-off is we have to use options wherever we need to represent a concept of something being there or not. So for example, we have our diff function here. Instead of throwing an exception where we try to divide by 0, we return an option. And if we would get an error, we return a none from that. Otherwise, we return the value wrapped in a sum. And this also forces us at the call site to handle the fact that this might fail explicitly, which is where we get a lot of this static error checking from. So, moving on from types, declaring functions. We've already met the main function. Main has no parameters and no return type. That second function there declares a single parameter x with type i32, and the return type is also an i32. That goes after the arrow. Just have a look at the syntax for that. It's a bit different from most languages. The third function there has two parameters, and a and b, returns an f64 as well. The fourth function there has a tuple of, the fourth function there returns a tuple of two values, sorry. So that's how we're using tuples here. We return two arguments at once. That's the zip function. Note that these two have no return statement. That's interesting. Rust is an expression language, so everything in Rust returns a value. Everything's an expression, even brace scope blocks. So your block that you start when you declare a function, that is a value and will return. So if you leave off the semicolon at the end of a block, the last line of your function will be returned automatically, basically, without a return call. Adding an expression with a semicolon is still required for every other line, but you don't need to do it on the last line, and that line will be returned automatically. This can take a while to grasp, and it's a little bit tricky to explain. And it's also one of the more complex bits of language, but this whole expression language thing, it lets you compose expressions really, really nicely, and it reduces a lot of syntactic noise once you get used to reading it. So there's all four shown to kind of compare them. So this is what conditionals look like in Rust. This is an if expression, not an if statement, it's an if expression. Should look familiar. You don't need brackets around the condition in Rust note. You can just leave those off. And I think the compiler will tell you if you leave them on needlessly anyway. So this is an example of using an if expression as a ternary. So because, again, if expressions return a value, we can bind the result. So also pay attention to how there's no semicolon after the 5 or 6 there, because we want to return the 5 or the 6 as the result of the if expression, and then that's all bound to an x. Rust has infinite loops built in, which can be very nice. They're usually used in combination with a break as well, because rarely do you actually want to loop forever in a program. This is what a while loop looks like in Rust. Should look pretty familiar. Again, you don't need the brackets around the condition. We also have for loops, of course. For loops are a lot more like Python's for loops or Java or C++ range-based for loops than your typical int I equals 0 for I is less than n, we can use them to iterate over a collection using iterators. We'll learn more about iterators later. But you do for element in A, and then it'll work just like Python. We can also use them to iterate over ranges. So that 1.10 syntax will create an iterator from 1 to 10, and then the for loop will iterate over it. We can also go backwards by reversing the iterator with the .rev function. There's loads of different functions we can apply to iterators to kind of compose them and stuff, but again, we'll get to that later. Strings. Strings in Rust are not very simple because they interact in quite complex ways with the ownership model and references and borrowing and stuff. Because strings can be very large. They can be arbitrarily large, so this involves lots of memory, and we don't want to be copying that willy-nilly. So we usually borrow strings. But we'll do that in more detail next week. For now, we'll consider the string type with a capital S. A string is a mutable variable length buffer in which you can store your characters. We can create an empty one with string : new, or create one from a string literal, which is a slightly different type, using string : from. From and new are associated functions that belong to a type. Think of them of like static methods for now. So string, if it were a class in Java, new would be a static method. That third line there declares a string literal, which has a different type to string, and we can create a capital S string from a string literal using the .toOwned syntax, which gives us ownership of the string. Those of you familiar with, again, functional programming, Haskell, will be pleased to hear we have pattern matching as well. Those of you not lucky enough to be familiar with Haskell might be a bit confused. Think of it as kind of like a fancy switch statement for now, or like a chain of if-else. So here's an example of using a pattern matching statement, pattern matching expression from the color enum earlier. We say match color, where color is the value that we're matching on. And then we check each of those match arms in turn until we get one that matches the value that we're matching on, if that makes sense. So if color happened to be red, then we'd return 25500. The value after each of those lines there is called a match arm, and the value after the arrow is what gets returned. Note how we have no return statements here either. The match expression will return one of those values at the end of the arms, and then because the match expression is the only expression in the function, the overall result of the match expression gets returned. So you can kind of see how those expressions compose there. Again, don't worry if that doesn't make sense, you'll get the hang of it. Pattern matching is, however, much more powerful than a chain of if-else statements, as it can also destructure values like this. So we're using match here to match on an option. So there's two variants to an option, none and sum. So we match on the none as usual. But what we can do is we can match on the sum, and we destructure it and bind the value in it to that variable I. So this maybe increment function matches on its argument. If it's none, returns none. If it's something, we return the thing plus 1. And we can kind of use that to pull values out of enums and rebind them and return them and stuff. This is where the power of Rust enums and pattern matching kind of comes together, and it makes for some really nice programming constructs that are hard to express in languages like C. And you can kind of see the usage of that in the main function there. So maybe increment will return sum 6, and none will return, the second one will return none. Pattern matching also has to be exhaustive in Rust, or the compiler will throw an error at compile time. You need to cover every possible value. So, for example, when we were using color and option, we covered every possible enum variant. But when we're matching on a number, for example, it's kind of inconvenient to cover every single possible case from 0 to 255 in the case of a U8. Or if we have an F32, we can't really conceivably cover every value. So that's where wildcard patterns come in. That last match arm there, the underscore is just a default case. So if none of the arms above match it, then it will fall through to the underscore and return that last one. There is a lot you can do with pattern matching. It gets kind of complicated, and there's a lot more bits of syntactic sugar we can throw in there to match on more complicated patterns. But again, you'll get the hang of it, and you will get the hang of it eventually, and you'll really like it, hopefully. Yeah, so that was a quick tour of some of the basics. Any questions? Felix?
What is printline put an exclamation mark?
Good question. I like that question. Printline is not a function. It's a macro. So where Rust functions can't have variadic number of arguments, which printline requires, so we use macros instead. Macros are kind of like functions, but instead of calling them and in the typical way function calls work, they expand. So the printline function call is replaced with some macro expansion based upon the macro rules for that macro. That's quite complicated, so don't worry about it too much for now. But wherever you see a function with an exclamation mark, it's a macro, and it's used a little bit differently to a function because it can have variadic arguments. But typically the only one you'll come across for now is printline or maybe the debug macro. Debug macro is very useful. Look that one up. Okay, if we've got no questions, any more questions, feel free to come talk to me or whatever. Bonus slides. We have bonus slides. So because we're going to go out to the labs and you'll do tic-tac-toe and eat pizza, but you'll need a little bit more before you can get some hands-on. So obviously you'll need to install Rust either on DCS or on your own machine. Rust is installed using RustUp, the Rust installer. Don't use your distro's package manager. It will likely be out of date. The link to rustup.rs, that's the website, and there's installation instructions on there. RustUp will download all the core components you need. You'll probably also want the language server. Rust Analyzer is the language server. There is another language server called Rust Language Server. Don't use that. It's old. Everyone uses Rust Analyzer. Notes on how to do this are at the top of the Part 1 notes on the MD book, so take a look at those. While I have written the tic-tac-toe to, as much as possible, be able to defer this conversation to next week, you will likely hit memory issues anyway. So here's the short version. Every value in Rust has an owner. When you pass that value around, the value is moved. So when you rebind the variable or when you pass something to or from a function, the value is moved. This is done as it allows the compiler to reason about memory management. If you want to use a value without taking ownership, you can borrow it using a reference. However, if we derive copy and clone for a type, so we tell the compiler, look, this type is copyable, then it's not moved and instead it's just copied. Today we're going to do that for all our types, so we don't have to worry about move semantics and borrowing too much. I don't want to stand here and info dump for an hour about the borrow checker as well as introducing all the basics. I'd rather save it for next week and do things more incrementally. So for now, copy and clone, don't worry about it. So this is how we derive copy and clone. Custom types in Rust can derive traits to get extra behavior for free. Pretty similar to how Haskell derives type classes. Traits in Rust are an abstraction used to define shared functionality, similar to interfaces in Java or Haskell type classes or Python's abstract-based classes. So the EQ and partial EQ traits let you use the equality operators, equal and not equal. Ordering traits let you use the comparison operators. Copy traits are the ones we're going to use. And the debug trait lets you kind of print a value in a debug representation. I'd recommend taking a look at Appendix C of the book. If you just Google the Rust book, it's the top result. Take a look at Appendix C. That talks you through how to do this. So yeah, if you write an enum or a struct or a type, put derive copy clone at the top of it, and that will tell the compiler, don't worry about the borrow checker, just copy everything for now, and we'll do it next week. Any more questions? Cool. So thank you very much, everyone. If you head over to CS, I think we'll be in 006. Yeah. 06. We have pizza. Log on and get started with tic-tac-toe. Thank you. Oh, one more thing. I forgot. If you need help with tic-tac-toe, we have lab tutors. That's me, Owen, Felix, Brendan, and Matt. Ask us for help and we can give you some help.